Well, we're going to talk about a number called e. I'm sure everybody's heard of pi before. I have it on the display here, written out to about 9 decimal places, and I'm sure you've probably heard that pi doesn't really stop here. Pi is one of those irrational numbers. It's not equivalent to any fraction. It cannot be written down as a finite or even a repeating decimal. Now, e is a number that's similar to this. If I pull up e here, you get a look at it. It's roughly 2.72. Like pi, it is irrational. It cannot be expressed as a finite decimal or a repeating decimal. The reason it stops or terminates here is because that's all it will fit on this display screen. But rest assured, both of these numbers have infinitesimal precision is what I would call it. It's a mistake to call them infinite. I mean, they're not infinite. Both of these numbers are smaller than 4, for example, so they can't be infinite. Now, what is e? How do you calculate it? What does it get used for? Those are some of the questions we hope to be able to answer. And then I'll take you through a variety of review exercises designed to help you begin to work with the number e. Okay. Let's suppose you were going to multiply 1 plus a half times 1 plus a half. That's easy enough to do. It's 1.5 times 1.5. You get 2.25. Now the idea here is we're going to multiply by more than just 2 factors. We're going to look at 3 factors and 4 factors and 5 factors and so forth. And you may be inclined to think that that's going to make the answer grow. Well, you're right. The answer is going to grow. But at the same time, we're going to make all the factors smaller. This has a value of 1.5. The next thing we're going to multiply is 1 plus 1/3, which only has a value of about 1.3. And we're going to take another one of those and another one of those. Will that be bigger than 2.25? The answer is yes, it will. Turns out to be about 2.37 to the 100th place. The next thing we're going to multiply together is 4 factors. But each of them will have a decimal value smaller than the previous one. So this was 2 factors of 1.5. This was 3 factors of 1.3, roughly. This is 4 factors of 1.25. Now, believe it or not, the answer actually gets bigger. Well, it should get bigger. We have more factors. But there are also factors that are smaller in value. So what does this make? I get about 2.44 to the nearest 100th. All right, fast forward until you have something like this. And how many of these do you have? Yes, you have 100 of them. Please do not ask me to write all 100 of those factors down. Why can't we just do this instead? Now, do I know what the answer to this is? I do not. But I have a machine here that can help. So let's type it in. 1 plus 1 over 100 raised to the 100th power. 2.7. Does that look anything like a number you saw a minute ago? No, you're not convinced, are you? Well, what if we did this instead? What if we did 1 plus 1 over 1 million? Which is just barely bigger than 1. And raise it to the millionth power. Let's take a look at that. That's starting to look like E, and that's really what E is all about. Now, you're probably not in a class where you've studied limits. I know my students haven't. But the whole concept here is if you let both the divisor and the exponent here go to infinity. Like this. Eventually, this calculation stabilizes into the number e. Now, if that's interesting to you, great. If it's not, well, that's too bad, because e is one of the favorite numbers in mathematics, and there are very good reasons for this. It's hard to understand these reasons, though, until you take a class like calculus. So today we're just going to learn to work with e and treat it like any other number. You can do a lot of math with pi, and you can do a lot of math with e. But mostly what you're going to do with e is you're going to use it as a base, both for exponentials and for logarithms. And today we're going to focus on exponentials that have a base of e. So let's get to it. Here's some example questions. How do you compute e to the third times e to the fifth? Well, just like with any other product of powers, if the bases are the same, you can just add the exponents. So this is going to be e to the 3 plus 5. 3 plus 5 is 8. That's e to the 8th. This next problem asks you to multiply e to the negative 4th times e to the 6th. And sure enough, all you have to do is add the negative 4 and the 6. The rule for dividing powers that have the same base is you're supposed to subtract. So you might take the 11 over 22 and simplify it to 1/2, reduce the fraction, and then write e to whatever 9 minus 10 makes. Well, that's negative 1. Now, I'm quite happy if people write this as an answer, but I'll also get textbooks who say you can't use any negative exponents. So they would want you to bring the e down to the bottom with the 2. And those are both correct, by the way. Let's see what else we need to be able to do. You need to be able to take the power of an expression that has a power of e in it. Now, this quite literally means multiply 4 of these together. So some students are more comfortable writing it like this. This is not the efficient, fast way to do it, but it sure works, and you'll probably get it right. Multiply 4 of these together. 4 factors of 5e to the 7x. Okay, what's 5 times 5 times 5? That's 5 times 5 is 25. The third 5 gets you to 125, and the fourth 5 gets you to 625. The speedy way to get here, the efficient way, would have been to just do 5 to the 4th. Let that exponent act on that 5. And then we're supposed to multiply all these e powers together. We do that by adding up all these 7x's. That's 7x plus 7x plus 7x plus 7x, which adds up to 28x. The efficient way to do this would be to just go 4 times 7. Another thing you might have to do is take a square root of an expression that has a power of e in it. Well, we know about radicals. Radicals of products can be broken up into products of radicals. And this one's not going to slow anybody down. The square root of 9 is 3. How do you handle the square root of e to the 6x, though? You might have more success with that if you replace the square root with the half power. And then just multiply the 6x and the half. Half times 6x is 3x, so you end up with 3 times e to the 3x. Let's do another one of these radicals, because I see we have a cube root right after this one. A cube root with an e power in it. Okay, break that up into the cube root of 8 times the cube root of e to the 12x. And I'm going to handle this just like I did the last problem. I think that cube root is well known. I'm not going to explain that. That's just a 2. 2 times 2 times 2 is 8. But here, Similar to the last problem, I'll take e to the 12x and I'll raise it to the 1/3 power, because then I can exploit the property where you take the power of a power by multiplying these exponents together. 1/3 times 12. 1/3 of 12 is 4. So you get 2 times e to the 4x. Okay, that's enough of manipulation of powers with e. The other thing you'll need to be able to do is look at a graph or identify the correct graph that matches an equation that is a power of e. Now, you can go to a graphing website like Desmos and get this figured out pretty quickly. But let's suppose you're stuck without a calculator and you just have to figure this out. Okay, let's use some logic here. E is bigger than 1. Okay? Powers of e are bigger than e. So if I let x increase, if I go to the right on a graph, and I take powers of e, the answers, the y's, should go up also. So you might be inclined at first to select one of these increasing graphs down here. But not so fast, because this is not really a power of e. It's a negative power of e. What difference does that make? Okay, well, remember this simple property. A to the negative k power is the same thing as 1 over a to the k. In other words, you could write this expression as 1 over e to the 2x. Now, a minute ago, I talked about how something like e to the 2x gets bigger as x gets bigger. Yeah, the bigger the x is, the bigger the e to the 2x is. But now that I'm dividing by it, it tends to make the overall answer smaller. So here's what you're supposed to learn. Yeah, either go put this into Desmos and see what it looks like. You'll see that I'm right. A negative exponent here generally means that as x gets bigger, y's get smaller. So I think it's one of these two. Now, how do I pick the correct one? Usually you can just plug a number into this and get the correct result. Such as, if you plug a 0 in here, plug in 0. 2 times 0 is 0. E to the 0 power is 1. Y is equal to 1. So when x is 0, y is 1. That matches this, doesn't it? That does not match this one, because this one, when x is 0, the graph doesn't go through the point of 1. And there's other ways to look at this too. But I would select this graph. And I could see that this is pretty complicated, and we should probably look at a couple more examples of this. So let's do that. This problem, similar to the last, has a negative exponent on top of the e. Okay, if I had 2 times e to the x, or any positive number times e to the x, if I didn't see that negative, I would immediately pick one of these increasing functions here. So as x gets bigger, y gets bigger. But in general, if you have a negative exponent up here above the e, you should do the opposite. You should pick one of these decreasing functions. Now, the question becomes, which one is correct? I'm going to use that same trick that I used in the last problem. And I'm going to ask the question, when x equals 0, what does y equal to? As predicted by this equation. So let's plug a 0 into here. I'll have 2 times e to the negative 0 power. Of course, negative 0 is 0. Opposite of 0 is 0. And e to the 0 power is 1. So you come up with y equals 2. Well, which one of the graphs down here has got the point 0, 2? Clearly this one. Not that one. On this graph, 0, 2 is here. And the curve misses it. You should pick that answer. let's do one more. Exponential growth would be when you have an increasing exponential graph. These are both exponential growth. These are both exponential decay. What do I have here? Growth. How do I know that? Well, generally you're going to have a positive number here. There's no requirement. But when you have a positive number here, all you have to do is look up at the exponent. If it's a positive exponent, you should have an increasing graph. You should have exponential growth. And they're going to make you pick between these two. So let me come down here and help you decide which one of these is right. Or pause the video and see if you can do it without my help. But I'm going to go ahead. You have y equals e to the 2x. Oh, I can see it's also times 3. Sorry about that. I'll write it down again. You're going to drop any number you want into here, but I think 0 is the easiest, okay? So the idea is you put a 0 up here for x, and it should help you figure out what the corresponding y is. So let's see. Y equals 3 times e to the 2 times 0 power. You know why I always pick 0? Because generally when you plug it into the exponent, you get 0 for an exponent, and e to the 0 power is 1. Y is 3 times e to the 0. E to the 0 is 1. So, when x is 0, y is 3. You should find an ordered pair on one of these two graphs, 0, 3. Is it this? No, that looks like 0.6 or something. Is it this? Clearly, that's 0, 3. So you're going to pick that one. Okay? And lots and lots of examples to look at like that. Here's one that asks about how a graph is growing or decaying. I think those are the words in the drop-down menu. If you're my student, you'll figure this out when you go do this online assignment. But let's talk about what we said a minute ago. Is this positive up here, this exponent? Yes, it is. So you should see exponential growth. Now it just becomes a matter of finding the y-intercept by plugging in x equals 0. So it's one of these two. Let's plug in a 0 up there. And 2 times 0 is 0, and e to the 0 power is 1. So we should have the point 0, 1. There it is. So we have exponential growth, and we have a y-intercept of 0, 1. Or perhaps they just want you to write 1 here. All right, there's one more type of problem I want to get to, and I've got about a minute to get it done. And it looks like this. They want you to rewrite an exponential function with a base of e in one of these two forms, and also to figure out what the r is. Okay, well, here's the one we're dealing with. And it's supposed to compare favorably to one of these two. Well, I think I figured out that a is 1. Otherwise, I would have some multiplication here that doesn't show. As far as whether it's plus r or minus r, I'm almost certain it's minus r. Because remember, when this has got a negative coefficient up here in the exponent, we're looking at a decreasing function, or exponential decay. So here's the trick. You rewrite this like this. You calculate this part right here on your calculator, and you set it equal to 1 minus r. So this equates to that. And then you just have to solve for r. Yeah, this is not something I think I can do in my head, so I'm going to do that on my phone, and I write it down to the nearest 3 decimals or so. So it's coming up 0.472, 0.4724. Okay, then you would subtract 1 from both sides, and you get negative r is equal to negative 0.5276. And so r must be 0.5276, like that. Now, about what percentage decay do we have? It is decay, it is decreasing. Well, if r is about 0.5, you may remember from previous learning that that represents about 52 or 53% decrease per time unit. Okay, which is just shift the decimal 2 to the right and you have it. Anyway, thanks for listening. My name's Eric. We'll talk to you later.